Imagine diving into a black hole, a space mystery that's like diving into a world of math puzzles hardly anyone explores. If you could actually journey into one of these strange black holes, you might end up in another universe. These cosmic monsters have a spooky dark circle at their core called the event horizon. Once you cross this line, there's no going back, like stepping off a cliff with no ground below. Black holes are like space vacuum cleaners sucking up everything, even light itself. Think about it. Famous scientist Michio Kaku is guessing about how black holes work, and new discoveries are giving us hints about the amazing secrets these giant space whirlpools hide. But what are they exactly? And why are they so powerful? These are the big questions that keep scientists scratching their heads, trying to figure out how gravity and the rules of the universe work. Black holes emerge from the remnants of deceased stars, born from the gravitational collapse of massive stellar cores. Their gravitational pull is so intense that even light succumbs to their grasp. Within the heart of most galaxies, including our own, lie these enigmatic entities, classified into 3 distinct types based on their mass. Stellar mass black holes, the smallest variety, form from the collapse of massive stars and typically weigh between 1 to 100 times that of our Sun. On the opposite end of the spectrum are supermassive black holes, colossal entities weighing millions or even billions of solar masses, believed to evolve through mergers and the consumption of surrounding matter. Intermediate mass black holes, occupying the middle ground, are a rare sight, weighing between 100 to 100,000 times the mass of the Sun. The Singularity, nestled at the heart of a black hole, represents the pinnacle of cosmic enigma. Here, the laws of physics appear to unravel as gravity exerts an incomprehensible force, pulling matter into an infinitesimal point of infinite density. The clash between Einstein's theory of general relativity and quantum mechanics further complicates our understanding, as scientists grapple with reconciling these disparate frameworks. Contrary to popular belief, black holes are not mere voids in space, but rather intense cosmic magnets, exerting gravitational pulls of unparalleled strength. Named for their seemingly endless descent into darkness, these celestial phenomena arise from the collapse of massive stars, compressing vast amounts of matter into infinitesimal volumes. The transition from a star to a black hole underscores the profound transformational power of gravity, challenging conventional notions of space and time. As scientists delve deeper into the mysteries of black holes, they confront the limits of human comprehension, exploring the intricate interplay between gravity, matter, and the fabric of the cosmos. In the realm of theoretical physics, the quest for understanding extends beyond conventional frameworks, with theories like superstring theory offering tantalizing insights into the nature of the universe. By positing a symphony of vibrating strings underlying all of reality, this theoretical framework seeks to reconcile the disparate realms of quantum mechanics and general relativity, shedding light on the enigmatic processes that govern the cosmos. While the true nature of black holes remains shrouded in mystery, they serve as gateways to a deeper understanding of the universe. As scientists continue to probe the depths of these cosmic anomalies, they uncover new layers of complexity, challenging our perceptions and reshaping our understanding of the cosmos. Understanding that black holes are mostly empty is crucial. The singularity in the center holds all collected matter, while the surrounding space is essentially vacuum, creating an appearance of deep darkness. Material and energy entering the black hole merge with the center singularity nearly instantly. The gravitational pull of black holes is enormous. Black holes cannot be seen because their power is so great that even light cannot pass through. Thus, scientists must use big radio telescopes and gravitational wave detectors to indirectly detect and investigate these mysterious cosmic events. Albert Einstein's 1915 theory changed our understanding of how moving things impact space-time. This remarkable revelation united space and time. Imagine disruptions on a peaceful pond. In 2025, a century later, the Laser Interferometer Gravitational Wave Observatory made a major discovery, the first ever gravitational wave observation by scientists. This amazing feat was achieved 1.3 billion years ago when two black holes collided. Black holes attract and superheat gas, dust, and stars, making their existence felt in the sky. Thermal traces indicate radiation from these components as they approach the black hole. The Event Horizon Telescope, a network of 8 terrestrial radio telescopes intended to photograph black holes, reached a milestone in April 2019. The first black hole shadow picture was captured. The black hole in the Messier 87 galaxy, a major component of the Virgo galaxy cluster, was the focus of this landmark photograph. The picture shows a bright ring around a black hole 55 million light-years away, with a mass 6.2 billion times that of our Sun. The bright halo is the tremendous thermal emissions from the whirling hot plasma around the event horizon, the black hole's furthest edge before it collapses under its gravitational pull. Theories of black hole travel imagine a human being swallowed by a black hole. It would have dire repercussions. No matter the black hole categorization, the prognosis is poor. A person that spontaneously enters a stellar mass black hole will undergo spaghettification, a terrible bodily metamorphosis. Despite its fanciful moniker, this occurrence is not funny. The incredible gravitational attraction of a black hole would compress and stretch the person, creating a spaghetti-like shape. Entering a supermassive black hole is less disastrous than other options. Let us examine it for the pursuit of scientific curiosity or as a great leap for mankind. The case of a person deciding to fall into Sagittarius A, a supermassive black hole positioned at the heart of the Milky Way, starts exploration. This celestial phenomenon has a calculated 44 million kilometers diameter and 4.31 million times the mass of our Sun. Sagittarius A exploration starts when a person passes the event horizon, a final frontier. Travelers can see their surroundings within this border, but outsiders cannot. External observers cannot see the person because internal light is captured and deflected inside. Despite the high gravitational pull within such massive black holes, the stretching effect is gentler, limiting the chance of spaghetti-like strands. Black holes' extreme nature makes direct observation and investigation impossible. Hence, these situations are speculative. However, black holes continue to fascinate scientists, helping us grasp the universe's complex mechanics. Escape from a black hole is difficult or impossible. However, white holes offer hope. White holes eject stuff, whereas black holes take it in. Thankfully, wormholes link black and white holes, albeit their nature is unknown. Although it would take billions of years, these wormholes may connect black holes to white holes. This notion must be acknowledged as theoretically explorable and refined. Kaku advises tempering expectations and avoiding irresponsible activities based on this notion. White holes and wormholes are intriguing and promising for interplanetary travel, but they are theoretical and need more research. Defying gravity in a black hole is a fascinating world to explore, despite its gravitational trapping. This setting allows experimental research to further human knowledge. These efforts may question the idea that stuff eventually collapses into a black hole. Planck stars, a loop quantum gravity theory, are an interesting option. Loop quantum gravity is speculative science, hence, it must be acknowledged. Its main goal is to provide a quantum framework to explain gravity. This approach quantizes spacetime into discrete, limited bits. They seem to move macroscopically due to their exceedingly small size. Spacetime granularity improves our comprehension of the universe in two ways. First, it provides a coherent quantum mechanics explanation for gravity integration. Second, it prevents black hole-centered gravitational singularities. Space's discreteness resists matter's collapse into a dying star due to gravity. This resistance limits matter's compression, preventing it from shrinking below the Planck length. Every object that enters a black hole is crushed but not reduced to minuscule size. Resistance stops compression, halting or reversing the collapse, which is more like a stoppage than an explosion. This suggests that black holes are fleeting and finite. However, from the outside universe, black holes die over billions or trillions of years due to tremendous time dilation. This temporal dilation reveals black hole holds vast time spans and cosmic dynamics. Gravastars are a proactive approach to singularities that avoids quantum gravity theories. Astronomy sometimes uses such naming practices despite seeming out of place. However, distinguishing a black hole from a gravastar is vital. The latter has dark energy, not a singularity. Dark energy, which permeates space and time, creates an expanding force. Even though it seems like science fiction, dark energy exists. Dark energy accelerates the cosmic expansion of our cosmos. Matter rushes into Gravastar, but thick-core dark energy prevents penetration beyond the surface. This contrasts with black holes, which have an event horizon from which nothing, not even light, can escape. Recent gravitational wave detector data by LIGO and Virgo during black hole mergers throw doubt on Gravastar. Gravastar mergers emit signals that differ from black hole mergers, causing ambiguity. These detectors keep collecting data, casting doubt on Gravastar. It's crucial to note that Gravastars aren't technically banned in our reality. Their theoretical base is, however, unstable and under review. Scientific knowledge and fresh observational evidence are crucial to determining the veracity of these theoretical constructions in our cosmic reality. An amazing finding about black holes was discovered lately. A newly discovered black hole devoured a star that came too near. A tiny galaxy a million light-years distant had a tidal disruption event, TD. The TD shined brighter than any other star in that galaxy after emitting a strong blast of energy. This has given scientists a rare chance to study black holes in galaxies. This discovery also introduces a new intermediate black hole for investigation, improving our understanding of their diameters. This cosmic evolution is intriguing and promising to improve our understanding. Scientists believe that supermassive black holes bigger than our Sun emerged from smaller intermediate black holes in the early cosmos. These intermediate black holes presumably lived in smaller galaxies and grew when they collided or were devoured by bigger ones. Most galaxies have huge supermassive black holes formed by this cyclical process.